we finally finished variacing the drive up. We got the capacitors fully reformed. It's now at full line voltage. We went ahead and connected it to the mains of the building, and now we've got 240 volt single phase powering up this ACS880. So this is the drive that we got for free. We cleaned it up, we static checked it, we made sure everything's good to go. And after we reformed the capacitors, now we have it completely powered up, and we're getting ready to spin that test motor. We've got a small motor here in the shop just to run it. We're going to verify a few settings in the drive. I know that this came from a metal stamping application. It was running a 40 horsepower motor on a stamping press for the flywheel, and we're going to be running it on ours here. So we're going to verify the settings. We're going to see what modified parameters are in this drive. We're going to wipe it, and then we're going to try to run this thing. So we're going to try to talk about a few of the things along the way that we've picked up about VFDs in the 15 years that we've been working on variable speed drives and motor controls. And then we're going to try to talk about some of the specifics for this ACS880 as well. So the first thing we're going to do is we are going to go into the parameters, and we're going to check and see what defaults, what changes from defaults exist. And so to do that, we're going to go to menu, we're going to go parameters, and we're going to go down to modified. This list shows every parameter that has changed from the default value. And in this case, we've got an external 1 command difference, which is for a 3-wire start-stop system. So the circuit that was controlling this through the digital inputs had a single pulse for start forward, a single pulse on a different input for start reverse, and then a maintain contact from a normally closed button on the stop input. So when the stop would open, the unit would accept the command and shut down. We've got maximum speed setting, a maximum current for the current limit. It looks like we have 208 to 240 volt, 94 amp, 230 volt, 60 hertz, 1775 RPM. So this is just the motor data. It looks like it was about a 30 kilowatt motor, so it should be 40 horsepower. And then the output phasing was actually switched in the drive. So you can either change the parameter from UVW to UWV to change the output direction of the motor, or you can swap 2 of the wires. But the simpler way to do it, if the drive has that parameter setting, you can just make the change here, and that's what they did. So that's everything that was in here. It looks like it was a very basic application. We want to go ahead and wipe that and start over. So we want to change a few things to be able to run our drive with no motor on it, and then also with this small test motor here in the shop. So we're going to go to complete list on this ACS880. We're going to go up to group 96, which is system. We're going to go down to 9606, parameter restore. We're going to edit that, and we're going to go clear all. Once we clear all, that's going to wipe the motor data. That's going to wipe any like accel decel rates, configurations. There's only a few things that it doesn't change, but for our purposes, everything is going to be back at default. So now we just clear that message. We're going to put in our new motor data here in a moment, but we want to go ahead and get rid of it. So no motor data. We're going to hide that. We're going to go back to our modified constants list, and we're going to see that there is no more motor data there. It says supply voltage, and that's the only thing that is set. So the first thing that we're going to do is we're going to try to utilize the assistant here so that we can tell it that this is the US standard, and that's going to set up, for the most part, it's going to set up our ability to program in horsepower instead of kilowatts. So it starts on international. We want to go to imperial and make that change. So once we go there, we can see, we can set our clock, we can set our date, we can set all of that. That's not really necessary for us here. We can go and program our motor data. And for our motor data, we're going to see exactly what's on the nameplate. So this one is showing it's a 3 horsepower, 230 volt, 7.6 amp, and 3450 RPM. So that RPM indicates that it's a 2-pole motor. Its synchronous speed would be 3600 RPM, but since this is an asynchronous motor, we have to account for the slip. So at full speed, full load, this thing will run 3,450 RPM. So we're going to tell it exactly what it is. We don't want to lie to the drive. We want to tell it exactly what the motor data is so that it has the chance to accurately protect it. We're going to say 230 volts. We're going to say motor current, 7.6 amps. So this is a great time to go ahead and switch us from DTC over to scalar mode. This is the direct torque control. This was common in the ACS 800s as well. This is the 880, and they're still using that DTC mode as the factory default, and it's very good for controlling, but not for a small motor here in the shop. And you cannot run this thing with no motor connected in DTC mode. So what we want to do is we want to switch over to scalar mode, and that will allow us to go into a volts per hertz. So if we give it a command to go to a certain frequency, at that frequency it outputs a certain voltage, and that doesn't change, and it's not trying to compensate for changes in the load like what DTC would. So we're going to go next. We're going to set up our min and max speeds here. We're going to go ahead and go to 0 for our minimum speed. And then because I have a 3,600 RPM motor, or 3,450, we're going to set this up. 3,450. We're going to make sure our max current is set way low because of our application. We are just testing here on a small motor. I'm going to crank it down pretty low and just say 30 amps. And then we'll go next. Naming the drive. I don't need to name it for this. Spin the motor. So we actually can't do that right now because we haven't connected the motor. So we are going to say not back up because we need to verify everything first. And so to run this thing without the motor connected, it's something that I like to do to make sure that the drive is outputting the right voltage and frequency, and make sure that all the phases of the output are nice and balanced before we connect the motor and potentially smoke something or just damage it. We just want to make sure that we're under control. And to do that, we're going to have to go into the fault functions of the drive. We're going to have to disable output phase loss. So to do that, we're going to go in, parameters, complete list. Then we're going to go and we're going to find our fault functions. I believe it should be somewhere around 30, group 30. It's limits, group 31, fault functions. So we're going to go down to 31.19. That's motor phase loss. It was set to fault. We're going to go no action. Now that we've got no action, we should be able to spin this in local mode with no motor connected. So you see here in the top corner, we are in remote. We want to go ahead and switch over to local. As long as my arrow is solid and I don't have any X's there, that indicates that my STO is enabled, and my DIIL, my interlock, and the run enable are all satisfied. So in the top corner, you see my speed reference is actually still in RPM. We're not using frequency right now. We're in RPM. So let's go ahead and hit start. Looks as if it's trying to start. And if we ramp up, you see our reference in the top corner is rising, and then the actual output that it believes it is, the motor is spinning, was rising as well. So we have another option here. We can go to options and we can say reference, and we can actually dial in the exact reference that we want. So if we want to go to 1,000 RPM, we can do that specifically, hit save. Now our reference goes up, we can exit, and the drive will follow its accel decel rate, and it will try to ramp up and accelerate to the commanded RPM. So once we get there, it's nice and stable. We're going to go ahead and use our Fluke 376 This meter is very specific about its sampling rate. It's a true RMS meter, and this is the only meter that we use for testing the output voltage of a VFD. I call that one my good meter because it measures all kinds of things, capacitance, it measures diodes. It's just a very good all around meter. But that even has a little bit of problems in measuring the output voltage of a drive, even with the low pass filter enabled. It's just not as accurate as what a Fluke 376 would be. So whenever we go here, we're going to measure across. It says 64.1, 64.2, 64.3, 64.2. So that looks very, very balanced. I would say that we are more than likely under control, but I also want to go up to full speed. So we're going to take this thing up all the way. We're going to go to 3450 RPM, and we are going to see that I actually have 230 volts on the output. So now it's ramping up. You can see we are going to be ramping up here. And once we get all the way there, we should see 230 volts. Like I said, it's not DTC mode, which is trying to compensate for changes in torque, changes in current and load. This is a voltage and frequency correlation. So you tell it to go a certain frequency, it goes that voltage. So 3450, 221, that's pretty accurate. So now we are going to go ahead and stop this thing. We're going to kill power. We're going to connect our test motor here. We have a small tachometer that we're going to use. We've got already a retroreflective sticker on the shaft. We're going to try to compare, and we're going to run it. We're just going to make sure that it's nice and under control. We're going to measure the output voltage of the drive. We're going to measure the output current and make sure that those are all balanced as well. Make sure that we don't have any funny noises coming from the motor, and just a general sense that everything is working properly. All right, we've got our motor connected now. We've got the drive powered back up. We're just going to verify that it spins correctly. It doesn't make any weird noises. It doesn't jump off of the table. We actually have it screwed in. We've got a lag bolt on the back whenever we're running a motor here so that it doesn't jump up. And we're going to start out kind of slow. So like I said, everything we got to be cautious about. We are going give it a command of 120 RPM, and we are in local mode, so we're going to fire it up. I've got a little piece of green electrical tape on it, and we should be running about 2 revolutions per second. So let's go ahead and test here. We've got our retroreflective tape. It looks like we are running 119.7 RPM. So for 120, that's pretty good for a scalar control mode. Let's go ahead and go up a little bit more. So let's go to our reference. Let's try 500. And let's see what we get there. Everything sounds pretty good. Looks pretty good. 499.2, 501, 499.3. So we are pretty close there. So we're going to go to volts here. We're going to make sure we're nice and balanced. I've got 32.9, 33 volts there, 32.9, and then U to V, 32.9, 33. So everything looks good and balanced there. I'm going to measure my current. I'm going to go to AC current here. I'm going to start with phase 1, 3.3, phase 2, 3.2, phase 3, 3.3. So we are still looking very good. We're nice and balanced. We're going to go ahead and run it up a little bit higher and just see what our accuracy looks like, the RPM that it believes it's going versus what we're actually measuring. Let's go 1200 RPM. We're going to let it get there. You see this is our commanded reference in the top corner, and then the large display here is the actual output. It looks like we're about there. 1200, and then let's hit our tape. 1201. Looks very close, very good. I'm going to say that this drive is a good drive, and we got a steal. We're climbing to 2200 RPM. $21.98, and nice and stable. So $21.94, $21.98 out of 2200. That's pretty good. So the drive ran the motor, no problem. Everything looks good. It appears to be a fully functional drive. And so in a normal startup scenario, if I were out in the field and I had finally got this thing running and programmed on the machine, there's one last step that I would want to do, and that's to back up the parameters and make a copy in the keypad. Now, this keypad is removable. You can actually move it to separate drives and actually transfer the parameters into a different VFD, or you can make a backup copy on this keypad so that if this drive ever fails, you can just replace it with the exact same model, download with the original keypad, and be ready to go. So the thing that we're going to want to do is go into the backup menu section. So instead of parameters, we're going to scroll down in the menu to backups. We're going to hit select. And this drive was previously used, so it already had 2 backups in there. That's fine. We can leave those. We don't have to get rid of them, but we want to create a backup. It looks like it can only store 2, so it says replace one of them. So I'm going to select the older one, and I'm going to replace it. So with the backup and restore parameters, we always have to be in local control mode. If we would have been in remote, it would have thrown a fit, and it would have made us switch over to local. Once it finishes that, the exact parameter structure with all of our motor data, accel, decel rates, units, everything that we have set up would be stored in here, and we could just pick right up where we left off. If we auto-tune the motor, that data would be in there as well, and our machine could be back up and running in no time. Once we have our backup completed, when you want to actually bring it in and restore, it's the same process. It's just in reverse, and instead of backup, you click restore. So once we have our backup, we can go back up, and instead of create, we can scroll down to the one that we just did. We can select it, and then as long as we're in local mode, we can go restore all parameters. And if we hit restore parameters, it'll go through the process of downloading them in here. I appreciate you sticking around for this process. We got this thing figured out. We got it all cleaned up and tested. And turns out we do actually have a good drive.